All right, now let's add the measurements. So we go to press the measure button, and we click add measurement, and then this button will allow you to select between source 1 and 2. I like to do 2 first, and then 1, this button here, you can kind of snapshot them all, but I want to put these to the screen so we can see what we're doing. So I want to add the frequency of channel 1 and add. I'll turn the menu off. And we can see the mean frequency is hovering around 100K, right? Then something is that sometimes when you make a change, the old statistics are there. So you go more statistics, reset, right? And then you can see. So if I were to, I'll just change the frequency a little bit, right? You can see, right, that yeah, the mean of the current value and the mean are kind of way off, and that's because the statistics are still remembering. All right, now it's, you know, it's closer. All right, so I'm just going to go back to 1 kilohertz. So let's add the other measurements. So we add another measurement. I want to measure, oops, still on 1, peak to peak. Okay, to add. I'm just going to turn off the menu just to make sure that it's there. All right, that's working. Now I want to add the peak to peak of channel 2. So I come up to source, change it to 2, and we'll add that. All right. And interestingly, we see that the peak to peak is kind of close to the channel 2 as it is to 1. Even though if you look at the waveform, it's kind of giving you an average by the intensity of where it sits, and you'd think it would be a little bit different. And so to get a more accurate measurement, we can do averaging. So we go back to acquire, mode, oops, and we do average, and 16 is good, right? And for this application, you can still see it changing around. And of course, we want to go back to measure and reset the statistics. Okay. So now, now we're seeing we're getting a much different value for the peak to peak of channel 2. So, you know, this is actually what you might call a finicky measurement, because we're taking the ratio of those peak to peaks on a log scale, and which can be hard to plot. Now, of course, we need to measure the phase. So we're going to add another measurement, and I want 2, and I want, oops, I want phase. And the important thing is to go from 2 to 1. Then you'll get the right sign that matches spice, right? And we'll add that measurement. All right. So now, you know, we're kind of ready to do our Bode plot. All right. Now, now the thing is if the low pass filter, the peak to peak of the output gets much smaller than the input, and so yeah, you have to scale to make sure that the digitizer is still getting the full dynamic range of the signal. But also there are some mighty strange things that happen at high frequencies, especially when the inputs are low. That's a whole other video. So really, just to avoid all that, I'm going to set the amplitude to 10 volts peak to peak, and you can see, yep, I need to rescale, right? But notice, actually at 16 averages, I guess it went pretty well. All right, but still, I always like to reset statistics. All right, so even though the frequency is the same, the peak to peak voltages mean it's about the same, right? At higher frequencies, you'll see that it's much better to start with a bigger input, because if the input is too small to begin with, when you attenuate it, you can attenuate it to where you're just reading noise. All right. Now, let's just take a few points. If I recall, the cutoff frequency of this filter should be about 1,731 hertz. So let's start off at 17.31. Oops. Hertz. And you can see the averaging kind of taking effect there, right? Which can be somewhat annoying. So sometimes what I do is I go back to high res to set up my measurement, right? And I'm not going to do auto scale, okay? I'm using the horizontal zoom button, okay? Oops. And again, you need to see a few periods so that you're getting it can find the automatic measurements. I'm going to go back to excuse me. I'm going to go back to average, measure, or actually just to reset the statistics. Okay, and so there's the frequency. You just write that down. Peak to peak 20.11. Excuse me. Peak to peak of channel 2, 20.07. And the phase, on average, it's 200 and change millidegrees, and yeah, it's bouncing around because that's somewhat hard measurement to take. All right, so that would be the first measurement, and then we can go up in decades into 170 point 3 173.1 hertz. Now I'm just going to not call it out every time. All right, and so we see the frequency has changed, the peak to peak of the input is still about the same, but write it down every time. As we'll see, the peak to peak output can change, and we're at minus 6 degrees or 6.7. All right, now let's go to the cutoff frequency, 1.731 kilohertz. All right, and I'm using the horizontal adjust scale. And now we're at peak to peak 19.84, and the output peak to peak is 13.53, which when you do that should be about minus 3 dB. But notice the phase should also be minus 45, but it's not. And what I've found is that phase is very hard to measure, and to get the minus 3 dB point exactly at minus 45 has been difficult. And what I find is that I know that this is a first order low pass filter because the non-inverting, because the phase is negative. I don't have to worry that it's exactly minus 45 at this point. I just know that it's negative, therefore it's a non-inverting amplifier, or excuse me, filter. All right, so now let's take it a decade higher. So 17.31 kilohertz. Zoom in. Now at this point, we want to increase channel 2, zoom in. You can see 500 millivolts, the scale. The peak to peak input is still about the same. The output, and we're approaching 90 degrees, minus 90 degrees. All right. So let's do 173.1 kilohertz. 173 kilohertz. Again, don't do auto because it's actually in this case harder. So I zoom in on the horizontal and I zoom in on the vertical. Reset. And we're getting minus 87. And we can still read, excuse me, the peak to peak of the output, right? But notice the input is starting to drop a little bit, and I'll explain that later. All right, so now 1.731 megahertz. Zoom. And now we're starting to see something a little bit more interesting. Okay. Let's see if I can. So I've zoomed out as much as I can on channel 2 with these probes that I have. 10 millivolts per division is all I can get. And it's telling me the peak to peak is 24, except you'll notice these kind of triangular waves, right? Especially in certain locations. And if I were to use a lower input voltage, I could zoom in on it. You'd find that these triangular waves are actually in the input, and it has to do with the digital synthesis of the function generator and the filter it uses. All right. So at this point, yeah, we might start to see some deviations from our prediction, even with the parasitics extracted with the impedance analyzer. But yes, the phase is starting to come up because we do have parasitic inductors in the passive components, all right, which, and now let's just take it to see what happens to 17.31 megahertz. And so it's saying I'm clipping, so it can't find it. And it's unfortunately the I mean, it's still digitizing properly, but the measurements kind of get in the way. Okay, so now notice the peak to peak is gone on the input from 20 down to 16. And that's because there's a 50 ohm output resistance that, now that the impedance of the capacitance is close to 0, is actually affecting the measurement, right? And at 20 volts peak to peak, right, we're starting to hit the current limit, even though I chose 2 kilo ohm resistor. So anyway, the phase is now positive, right? And the amplitude is higher than it was before. And if you look at the Bode plot of the low-pass filter with parasitics, we're effectively seeing that. Now, at these frequencies, you can see that there's distortions in the sine wave. You can see even me like waving hands over it as I affect the circuit. So, but there you have it. We have a Bode plot the measured should match the theory of the Bode plot we calculated with LT-Spice when we used the parasitics that we extracted with the impedance analyzer. Now, I would be remiss in my duties not to talk about rise time. So I'm going to change to a square wave, and I'm going to go back to 100 hertz. And this time I will auto set. Okay. So if you notice, right, this is a square wave, and there's this rise time. It's a little hard to see on this scale, so let me zoom. And I'm going to push this up here where you can see it. Pull that down. Okay, and you can see that it takes a certain amount of time to get from 0 to full max. All right, and if you want a more accurate measurement, you try to zoom out and then pull that over. Now what I'll do is take a quick measurement on channel 2 for rise time. So we'll do measure, add measurement. I want the rise time of channel 2, and I'll just snapshot them all. And I was able to get a rise time of 178.9 microseconds, and so the rise time is measured from 10% to 90%, and there's a calculation that you can turn that into tau. I'll put that in the manual. I derived it out, but again, that's in another video somewhere. So anyway, that rise time can give you the RC time constant of the filter, okay? But you can see that the parasitic part might be hard to determine because the rise time is so long that you're trying to digitize the frequency component, the high frequency component of that part of the filter, or how that response. But the thing is if we call this time equals 0, that's actually, if you convert it to a Bode plot, would be high frequency or infinite frequency. And over here at long time, that would turn into DC. So if I wanted to kind of see what's going on here, I should be able to zoom in on it. Okay. And in order to see what I'm doing, just remove everything. And you can just see that it's I don't think my camera will show it, but there's just this little bit of ringing. But there's also ringing here, which turns out that this is all calibrated, but that 50 ohm resistance, when I put into this low pass filter with parasitics, turns the input node into kind of its own filter. That's why you have to measure the input every time to scale it for the Bode plot. It's probably a little bit much for now, but Bode plots are at high frequencies can be tricky to measure. The thing is even though we measured at these high frequencies, I'm just going to do auto set. Many times, all you really care about is that kind of first order response, that rise time, right? That's the big point. Now, what can happen is when you put it in a feedback circuit, all of a sudden, those high frequency components can come back and haunt you, if you will. Now, the bottom line is, if that's important, choose passive components that don't have as much parasitic. That's the fix there, is just don't use them if you don't have to. Or they're more expensive, so you use the appropriate passive devices for your need. Okay, that's it.